The same chapter, graph. Oh, sorry. Okay, now let's talk about graphs. How, what they are used for. We'll be looking at an example here. What type of graphs we have. So for example, weighted graphs, directed graphs. We'll look at an example of how to make a graph for considering this example over here. And we will also see what these two-dimensional arrays or tables represent with respect to these graphs. Okay, so very interesting stuff. These graphs basically create the foundations of problems involving me going from one source to a destination and finding the best possible path from that source to a destination, right? So this graph over here, this basically, it can be used to represent a relationship between different things. In this particular example, this relationship is actually the connectivity between different parts in the London underground map. So for example, if I want to connect different parts in London based on their connectivity routes underground, this graph represents that I am connecting from part A to B directly. And if I want to access part C, I will have to do it through either B or some other path, so on and so forth. There's a direct connection between D and B, D and E, so on and so forth. So basically this graph represents, in this particular example, okay, what parts of the London underground are connected to each other either directly or indirectly. And what will that do is that if, for example, I want to take a train from B to D, I can take it directly because there is a direct path. However, if I want to go from B to F, there is no direct path from B to F. I will have to either access F through C this way, or I have to access F through E this way. Now, which is the better choice of this? That can be determined much easier, in a much easier way, if I have, say, a weighted graph. Now, this is what a weighted graph means. Basically, weighted graph tells me two things. First thing, it tells me, like before, that what parts of London, for example, or the underground stations of London are directly connected. It tells me that. So as before, that's doing that. Apart from that, is also telling me the cost of traveling from one part to another part. By the way, these parts in a graph, this is known as a node. These vertices that are connected to these are known as nodes. These are nodes. And the path that exists between these nodes is known as an edge. So this is the edge, and these are the nodes. So as you can see in this weighted graph, these edges are labeled. And this value represents, these weights represent the cost of, say, traveling from this node to this node. Now, this cost could mean multiple things. But in this particular example, since we actually have traveling on a train between different parts of the London Underground, this cost could represent time. Now, again, it's a very vague term. This time could be hours, it could be minutes, whatever it is. But again, it's just the cost, right? And whatever that cost I'm using here, if the unit I'm using here is hours, it's hours all over. If it's minutes all over. So whatever standard unit we choose, we're going to be applying it for all over. So, but the generic term that's applied here is cost. So what I have to do is that if, for example, I have to find the path from B to F, I have two choices. Since there is no direct path from B to F, I have two choices. Either I can travel from C or I can travel from E. Now, which one of my paths will be chosen? Obviously, the one with the least cost. In this case, that would be from B to C, then C to F, so which is 3 plus 2, 5. On the other hand, if I use this path, it's 4 plus 3, which is 7. So the cost here is better. Usually what the case is that the direct path, if a direct path exists, that is the optimal solution. So in this case, B to D exists. But there is a great chance that the direct path actually costs more. It's possible. The direct path costs more as opposed to, say, for example, using two other edges. So let's just say, for example, the direct path between B and D causes is taking up space, is the cost of driving from B to D is 10, just for example. So if I take the direct path from B to D, my cost is 10. However, if I travel to D through, say, E, my cost is 6, which is even lesser than through B to A. So in that case, the shortest path is obviously from B to D. So it's not always the case that the direct path is always the shortest path. It seems like it's the easiest, but it's usually not the case. So in any case, our priority is given to the path. If there are multiple paths, our priority is given to the path that results in the shortest cost, the smallest cost. A second version of this graph is known as a directed graph. Now, this was the weighted graph. This is directed as well as weighted. Now, as you can see here, the edges here are, apart being labeled with their weights, they're also showing which directions are possible from each connecting node. So as you can see here, I can travel from A to B, and I can travel from B to E, A back as well. And the cost is same, which is not always the case. The cost necessarily doesn't have to be the same. Now, you can see here that traveling from E to F and F to E is possible, but the cost is different. Why is the case? I mean, it doesn't say anywhere that the path that you're using is the same one. It just means that there is a path in both directions. So what that means is that maybe, let's just say in terms of roads, for example, there is a road between E to F, and there is also a road from F to E. But for some reason, the road from E to F is shorter than the road F to E. Say, for example, there's some obstacles, there's a mountain in between or hills in between, because of which the road has to slightly curved outward, resulting in the path from F to E becoming a little longer. And that's possible. But this basically is showing that there is a path existing between traveling for, allowing for traveling in both directions. And since we're using a directed graph, it makes one thing very clear, that if, say, for example, I'm allowing both direction travel, I will have to have clearly labeled it so. So for example, here, as you can see in this particular example, traveling from D to B and vice versa is possible because it's labeled this way. If I have not labeled in both directions, it is automatically assumed that only one direction, either is labeled this way or this way, only one direction is possible only. The other direction, it cannot be carried out. And this is what directed graph makes it very abundantly clear. So what that means is that possibly there is a one-way road between D to B. And if you want to come back from B to D, you'll have to use some alternate road, because that road that you just used from coming to D to B is a single direction road, and you cannot go back on that road. And you will have to take some alternate route back. As you can see in this example over here, this is again directed weighted graph, but in this case, this highlights the exact issue that was being pointed out just yet, that if, for example, I travel from D to B, there is no guarantee that there is a path back from B to D, as it's not mentioned here. So if, for example, I happen to go from D to B, to come back to D, I'll have to find some other path. Now that could be through either E or through A, whichever is the shortest round cost. Obviously, it looks like traveling from B to E, then E to D is resulting in 8 also, whereas B to A and A to D also resulting in it. So I guess though both paths are equally, costly, it's not the same cost, moreover. But there is no direct path between back from B to D as mentioned here in this directed graph. Now, let's just consider these examples. If using this figure over here, if we want to travel from C to D, This is C to D. We can either use the option B, C to B to A and D, which will cost me around 3, then another 3, then back here 5. So that's a total of 11 minutes. If they say, for example, this was 11 minutes, if this unit was used being 11 minutes. So the cost from C to B to A, then E is 11 minutes. On the other hand, if I come from C to D using this path, that is 2 minutes to F, another 3 minutes to E, then another 4 minutes to D. So that means 2 plus 3, 5 plus 4, that's 9. Obviously, this saves me 2 more minutes. So if I were to travel from C to D, since there is no direct path, I have two options, C, B, A, D, or C, F, E, D. In this case, C, F, E, D seems like a better option because the cost in terms, in this example of minutes, is much less. Now, considering this example over here, we have to label this graph based on this description here. So seems pretty straightforward. Let's try this out. Now, first description, it says that, yes. The first description, it says that there is a path from A to B, which is 2 kilometers, and it's only a one-way system. So that means it is weighted and directed. So in this case, this is only 2. And yeah, by the way, you notice that this is now the cost being used is kilometers. In previous examples, it was minutes. It could be anything, but just in terms of cost, okay, it could be anything. Secondly, it says there's a path from D to A, which is 1 kilometer and it is in one way. So again, we will make a path from D to A. And again, the cost here is 1 kilometer. And this is only one way. So there's no way of coming back from A to D directly. Secondly, I have a path from B to D. Again, this is one way. So B2 directed weighted graph like so. And this is only direction from B to D. And that is 3 kilometers like so. Finally, we have B to C, which is 4 kilometers. Now, as you can see here, it has not specified that it is one way or two way. So I guess we can add it both directions. So in this case, we can say B to C is 4 kilometers. And C to B also exists. And that could be also 4 kilometers. Like so. So even if, say, for example, we don't add the second arrow, since it has not specified it's one way or not, even if we add not an arrowed line, an undirected line, with simply saying the edge is 4, that should also suffice. For example, now it says it's C to E is 7 kilometers. So again, there is no specific direction mentioned here. So that means a direct path just like this can be made, and it's not directed. I'm not using arrows because it's not specifying any what you call directions. In this case, there's a direct path from C to E, and that's 4. So assuming that we can both move in both directions. Similarly, if I go to D to E, again, there's no mention of direction. I can simply add this edge, and it's 5 kilometers. So again, just to keep up with the pattern, let's also change this. You can call this as only a single line like so, because it's not specified the direction. We'll call this as only 4 kilometers. So considering this, by the way, yes, I think we should add directions because it's saying it's a directed graph. So I guess it should be both directions. So let's just make it short like this, even though there should be a different path, but you get the points. Like so. So we can either do this or we can draw a separate line altogether like this. can do this as well. And this reverse direction as well, like so. So we can also do this as well. We have draw another line, say in this direction, like 4, and we will erase this and call this line directing, pointing towards the other direction. Like so. Same thing goes over here. We'll draw another line pointing in this direction, like so, and erase this part over here. So considering these specifications, I guess we can use this graph that follows the specifications mentioned here. Okay. Now, moving on. Okay. To implement a graph, we can use an adjacency matrix or an adjacency list. Now, as you can see here, these are two. This is the matrix and this is the lists that we're talking about. Okay, now let's look at the adjacency matrix versus the cost matrix. Now, what this represents is that, as you can see here, this mentioned over here, the same diagram that we're talking about, I think, with respect to, yes, the 2309, this diagram over here, So basically what adjacency means that is there a direct path between two vertices? Now let's just say, considering vertex A is directly connected to both B and only D. So as you can see here, for A, it's connected to B, yes, and D, yes. So any vertex that A is directly connected to, there's a direct path between, I will give a value 1 to it, otherwise everything is 0. Same thing goes with B. Now for B, I'm connected to both A, D, E, and C. So as you can see here, for B, I'm directly connected to A, then C, then D, then E. As mentioned here, see, B, I'm connected to A, then C, like so, and then D, and then E. Same thing goes with C. Now check it out. C is directly connected with B. C is directly connected to F. So C is connected to B and then F. Same thing goes with D. D is directly connected to A. D is directly connected to B, and D is then connected to E. Finally, F is directly connected to only C and then E. So this matrix is simply representing if whether I am directly connected to a particular vertex, true, or if I'm directly not connected to a different particular vertex with labeled with a 0. Now, as you can see here, that any vertex that I'm not connected to, including the vertex on its own, is labeled as 0. So A is obviously not connected to itself, that's going to be by default 0. Any other vertex that it's not connected to will also be labeled by 0. Okay, this is another adjacency matrix. Now this one shows something else. This basically only represents the cost values. Now, as you can see here, there is a direct path between A and B. Is it mentioned here? Yes, there's a direct path between A and B. And as you can see in this label diagram over here, this weighted graph, there is direct path between A and B, and the cost from traveling from A to B is 3 kilometers, minutes, whatever it is. There's a direct cost between A and B. So as you can see here, if I travel from A to B, it is possible, and the cost of such a travel is 3. Similarly, there is a direct path between A and D, and the cost of such travel is F. Any other path with which I'm not directly contacting with, there is no directed path with, I will simply label that as infinity. I don't know the cost. There is no direct path, so I really don't know the cost, what it is from traveling from A to say C. there is multiple edges, so I don't know the cost of it right now. So for the time being, I'm labeling it as infinity. So any edge, any vertex that are not directly connected to will be labeled as infinity as the cost. Same thing goes over here. As you can see here, the B, there's a direct link with A, yes, the cost is 3. Direct link with C, the cost is again 3. Direct link with E is again 4. And any other path, including B itself, is labeled as infinity, is there's no direct link. So the difference between this diagram and this diagram, or this adjacency matrix, is that this one is for figure 23.09, which is simply representing which vertex has a direct edge between it or not. There is no mention of any cost. Whereas this one, on the other hand, shows the weighted graph of the same London underground map. Now, in this case, if I don't have a direct link, I will label that as infinity. If I do have a direct edge passing between two vertices, I will simply write the weight value of that particular edge. Okay. Next mentioned is the list. Now, the list goes something like this. Again, for figure 23.09, which was originally mentioning only which path directly exists between adjacent vertices or not, only mentioning the edges connected or not. So as you can see here, that there is a direct path from A to B and D only. They're directly connected to B and D. From B, there's a direct connection to A, then C, then D, then E. There's a direct B, there is a direct connection to A, C, D, and E. See, that's mentioned here in this list. Similarly, there is a direct link from C to B and F. There's a direct link from D to both A, B, and E. Finally, there's a direct link from E to B, D, and F. And from F, there's a direct link from C to E. And if I look at the weighted graph, so this list represents the weighted graph of 23.05. Now, there are two readings here. As you can see here, from A, there's a direct link to B. Now, if you can see this version over here, this B represents the vertex that this vertex is directly connected to. And this second value represents the cost of traveling from this vertex to this. And each vertex that I'm directly connected to with this one is separated by the column. So I basically am connected to two vertices with A, that is B and D. And direct communication from A to B is cost 3. And direct communication from A to D is cost 5. Same thing goes with all other vertices. There is a communication direct link with B to A at a cost of 3, B to C, cost of 3 again, B to E at cost of 4, so on and so forth. So basically, this matrix is basically representing two things. One, which vertex is this particular vertex directly connected to one? That, by the way, is also being done over here. But this table is for 2312. And 2312 is actually a weighted graph. So this basically represents what vertex am I directly connected to, and the cost of being connected to that vertex. It mentions both things, the direct connection as well as the cost. So basically, this is representing your neighbor. Okay, now let's talk about one example over here. At the end, it's saying construct an adjacency matrix and adjacency list to represent your graph for task 2309. Now, 2309 is this one. We are to create an adjacency list like so, and adjacency matrix for this particular task. Now, do you think that's possible? Let's check it out. Okay, so the example states that we have to create the adjacency matrix. Now, this is basically the matrix for this 23.09, and this is the adjacency list for the same graph. So as mentioned before, there are direct links between A and B, B and C, C and E, E and D, and B and ED. So these are the weights. This is a weighted graph, as mentioned before. We're ignoring the directions because that's not required for both the adjacency matrix as well as the adjacency list as we saw in the example as well. Now, based on this, we got the adjacency matrix like so that we can see that there's a direct link between A and B, and the cost of A and B is 2, and there's a direct link between A and D, the cost of A and D is 1. The rest is labeled as infinity. There's no direct link between A to C and D. Similarly, for B, there's a direct link to A, which is 1, direct link to C, which is 4, direct link for D, which is 3, and B to E is infinity. There's no direct link. And as mentioned before, any link with its own vertex is always labeled as infinity. C to A, no direct link, infinity. C to B is labeled as 4. C to C, infinity again. C to D, there's no direct link, infinity. C to E, that's 7, like so. Finally, D to A is 1, as you can see here. D to B is 3. D to C is infinity. D to D is infinity. And D to E is 5. Finally, you have E to A is infinity, no direct path. E to B, no direct path. Infinity. D to C is 7. Sorry, E to C is 7. E to D is 5. And finally, E to E is also labeled as infinity. So this is my adjacency matrix. This is my adjacency list showing the weights plus the directly connected vertices. A is directly connected to B at the cost of 2 and directly connected to D at the cost of 1. B is directly connected to A at cost of 2 and C at the cost of 4 and D at the cost of 3. C is directly connected to B at the cost of 4, E at the cost of 7, and D is connected to A at the cost of 1 and B at the cost of 3 and the E at the cost of 5. And finally, E is connected to C at the cost of 7, D at the cost of 5. So these are the same things, adjacency list and adjacency matrix as requested by the book for this exam.